Thank you so much, David, for that kind introduction. It's really great to be here. Thanks for the invitation. Look forward to some interesting conversations this afternoon to see some old friends and colleagues. Right, so playoffs. So I wasn't sure what to present today because, as David mentioned, our research in my lab is quite broad, ranges from neuroscience to applications of computer vision. But I just decided at the last minute that given some of the translational objectives of vector and also the broad interests of people at vector, I would present more of an applications talk that I hope you find interesting. So it's not going to be super technical, but I hope I'll raise some issues that are interesting. And please interrupt me with questions or comments anytime, very informal. So before I get to hockey, I have to put in a shameless plug for, if I can advance the slide. Let me try to replug this. Oh. Okay, sorry. See if I can get back where I was. Sorry about that. Okay, there we go. Shameless plug. We have a conference coming up at York on predictive vision in June. Great lineup of speakers. Again, ranges from neuroscience to computer vision. So if that intersects your interests, I'll just bring to your attention, we have a call for poster abstracts. It's still current. Deadline is April 23rd. Just up the subway line, very short commute. So if it interests you, please come up and take part. Very reasonable registration fee. Yeah, so I am going to get to hockey, but there's going to be some introduction to that. So first I thought I'd give a bit of introduction to the lab, going a bit beyond the things Dave said. Then I kind of want to set up the hockey talk with a preparatory section on what I'm going to call attentive video, okay? So this kind of deviates from the work on contours and shape that Dave talked about. So I want to set that up for people. And then finally, I'll get around to hockey. So don't worry, I'll get to hockey. But first of all, just to introduce you to the lab. So we have kind of a motto or a creed, which is improving machine vision systems through a better understanding of biological systems. And so consequentially, we have quite a mix of people in the lab coming from computer science, engineering, but also from neuroscience. And so the philosophy is as follows. Why should we have to look at biological vision to build good computer vision systems? So I think we've all seen in the last 10 or 20 years a real coming of age of computer vision in the sense that we have lots of good applications that work well to solve important problems. And that's largely due to, I think, this integration of computer vision with machine learning. But I think it's still fair to say that there's still a difference between typical computer vision systems and biological systems. And in particular, when we build a computer vision system, we usually engineer that quite specifically for a specific task. And that makes good engineering sense, right? You want to really focus on the problem at hand. What we find in biological systems, on the other hand, is biological systems tend to be quite general in the sense that, for example, you and I, from moment to moment, will have to maybe be doing multiple visual tasks at the same time. You know, we'll have to understand our three-dimensional context, recognize objects, maybe navigate, manipulate objects, and so forth. And so far what we know about neuroscience is that we don't have a specific network for each one of those tasks. There is modularity, but there's also a lot of sharing of resources, and probably something closer to a generative model than a discriminative model. So the claim is, or the philosophy is, as we are moving more toward more general purpose AI systems for many applications like social robots, where we need machines to interact in more flexible ways, in more diverse ways with humans, it makes sense to be trying to understand how these more general biological systems work. That's kind of the overall philosophy. So we could talk about this all afternoon, I think, but I'd like to throw up some ideas about some of the principles that are important for biological systems in achieving these objectives. And I'm going to focus on two of these that will become relevant for today's talk. And these are attention. So humans, for example, are very active observers, and also 3D. So I'm going to make the claim that humans just always, or almost always, just do everything in 3D, even though images are themselves 2D. Before I actually get to the substance of the talk, let me just run through some of the projects that I won't talk about too much to give you a sense of more of our AI side. So we have kind of this neuroscience side, but on the AI side, in relation to that 3D dimension, we're very interested in single view 3D perception in particular. So in the near field, you can use your two eyes, binocular vision and motion parallax, to get a lot of 3D information. But as we move to the far field, these cues become quite weak, and humans begin to rely much more on single view cues. So that's interesting to us, and it's very important for a lot of different applications. So that's something that we're working on. Happy to chat about it afterward. It won't come up too much in this talk. What will come up a little bit is this recent collaborative project we have called iSum, which is really about how do we harness all the video cameras we have now in place in urban environments and do something good with them, do something useful. And one of the things we think we can do is better understand how people move around in complex urban environments. And that could be relevant to, for example, things like Vision Zero in Toronto, where we're trying to cut down on the number of pedestrian fatalities. It could be relevant to making our transportation systems more efficient and so forth. Okay, getting more toward this talk, what I'm going to talk a bit more about is attentive sensing. So we're interested in building novel kinds of machine sensors that can attend to the world around them in the way that humans attend. And then that will lead to this fun project, this applied project on sports videography. All right, so that's the intro. So as I said, there's going to be kind of two courses. It's a lunchtime talk, so I thought I'd serve an appetizer, and then we'll have the main course after that. Okay, so the appetizer is attentive video. I essentially want to kind of build a bigger framework for the hockey project. So what's attentive video? I think we have an opportunity. We have billions, literally billions of video cameras out there, and a lot of them are kind of on 24/7. So we have this enormous stream of bits flowing out, but almost all of those bits are just spilt onto the ground, basically. These data are not really used. And so the question is, can we make better use of video data? And obviously, to do that, we need to somehow curate this information and extract value from it. And attention is one of the dimensions of that process, we think. So attention has many forms, but for example, you think about spatial attention, just being able to move cameras intelligently, so pan, tilt, zoom, to be looking at the right thing, digital zoom to select the appropriate spatial aspect of parts of the video stream, temporal attention, so extract the temporal segments that are interesting. We need a way, first of all, because the quantity of data is way too big to move and to store, we need to cut that down, but we also need to be able to extract the valuable part, both for just for delivery to the human perceptual and cognitive systems, but also for downstream analytics, right? We need to kind of deliver only the parts that are important. So that's the overall philosophy. And we can think about how that is important in different application domains. And I'll end with sports video, but let's start with a couple of others. So visual security is kind of an obvious application domain. where attention is important. So in a typical visual security system, the goal is to maintain visual contact with an entire visual environment. So it could be a big room, it could be a plaza, it could be an intersection. At the same time, you have some kind of requirements that you're able to perform some inferences. So for example, it could be identity, it could be activity recognition, and so forth. And as we all know, these are conflicting goals, right? Because the more you spread out the resolution of the camera, the fewer pixels you have to perform those localized tasks that you need to perform. That's a classic trade-off. So the natural thing to do is to look, well, how do other systems solve this problem? Okay, and the interesting thing is that this is a fairly natural human visual task, maintaining visual awareness while still being able to perform, tasks of recognition and so forth. So what's evolved in the human visual system, as you know, is we have this amazing wide field of view. It's more than hemispheric field of view. So we maintain very good visual awareness of a very large part of our visual environment instantaneously. And of course, if we had a standard kind of CMOS sensor, that would be bad news for resolution, right? We'd have very poor acuity. But as you know, the solution that evolved was to not have a uniform sampling, right? But to have a very, very non-uniform sampling where we have a very high resolution fovea in the central 1 or 2 degrees of your visual field. And then that falls off exponentially with eccentricity. So it's, again, trading off this, these dual requirements of field of view and acuity. And finally, of course, all this would be useless if it wasn't for this very high performance oculomotor system that we have. So we can orient very quickly to the things that we need to orient to, right? So you need to have an attention system which tells you, okay, this is important. And you also need to have the motor system that can orient you toward that. All right, so that's the way the human system evolved and operates. And we've been interested in, for a number of years, in building simple sensors that can kind of achieve the same thing, albeit in different ways. And this is a recent example. It's I don't know how well you can see this, but the critical idea is to closely couple two cameras. There's one camera at the bottom here, which we call the pre-attentive sensor, and there's a second camera here, which we call the attentive sensor. And the pre-attentive sensor has a wide field of view, so that's what you're seeing in the top image, top video there. And it's fixed in space because it's assumed that its field of view is sufficient for the visual environment. But this second camera has a longer focal length, so much smaller field of view. And it's also fixed in space, but we have these two mirrors here, we call the pan and the tilt mirrors. And so it's a double bounce system, so light rays bounce off the pan mirror, then bounce off the tilt mirror, and then into the attentive sensor. And as you probably already figured out, the advantage of this is that these mirrors are extremely light. They have a very low moment of inertia. So we can very rapidly move these motors and deflect the gaze of the attentive sensor. Okay, and so that's what you're seeing at the bottom here, where we're just running an open source deep face detector, and then the attentive sensor is controlled to fixate these faces. Now in this particular demo, we're running at a lower fixation rate, but we're now operating at about 6 fixations per second, which is superhuman. So you and I would saccade maybe 2 or 3 times per second. And we're on our way, I think, to about 10 or 12 fixations per second. So it's kind of an interesting device. And so why is this important? So this is just in the lab, right? So these students are maybe 3 meters from the sensors. So in this case, having that attention mechanism is not super important. But if we go to a more realistic scenario, so this is an indoor example. I don't know how well you can see this, but an indoor example at about 21 meter range. It's not a crazy distance. And these are kind of the standard 2K cameras you would use for most applications. Even at 21 meters, you can see in the pre-attentive field of view, so these are faces that were automatically detected, and then fixated by the attentive sensor. So face detection works at that resolution. But if you start to require identity recognition or expression recognition, then that's now becoming challenging at pre-attentive resolution. Whereas you have it's a bit low contrast here with the light, but with the attentive resolution, you have much more information. This is at 27 meters in an outdoor environment, and you can see probably clearly you get a lot more information from the attentive stream. Now, a question we often get asked when we talk about this work is, well, why don't you just use a higher resolution camera, right? Why have all this mechanical stuff? It always reminds me of this apocryphal statement attributed to Bill Gates that, 640K memory should be enough for anybody. The answer, there's several answers to that question, but one of the answers is there's always a need for more, right? So no matter what your resolution, your 4K camera, whatever it is, there's always some use case of extending that range further. So that's one of the answers to that question. Okay, so that's one of the ideas about what I'm calling attentive video, one of the use cases. Lots of interesting challenges that I won't talk too much about, but there's good opportunities, I think, for the application of reinforcement learning in this kind of paradigm, because you have these two different cameras with different abilities. So you have more information essentially coming from the attentive sensor. So when the pre-attentive system makes a saccadic decision, the attentive system can provide feedback on whether that decision provided reward or not. So there's certainly some opportunities there. Okay, so the second use case I wanted to touch on, at least, was in this area of urban mobility, which is really the topic of this ISOM project that I mentioned. And so that project is really about trying to address some challenges we face, I think we all know too well, in the GTA. So you guys have the luxury of working in this fantastic downtown location, although Corrette has to commute from Hamilton, but I work at York, so I commute every day from the west end of the city up to York. So I'm intimately familiar with problems of urban mobility. So big economic cost, big cost to environment as well, and lots of concerns about accessibility, particularly as the demographics change in Ontario. We have a very good and ambitious plan for accessibility in Ontario, but we're not very far along the way of realizing that plan. And so this project is about trying to bring together different components of intelligent systems to try to provide more awareness of how people are moving around in urban environments, and hopefully inform both management and planning of cities. So it's really about bringing together computer vision people, geomatics people, computer graphics and simulation, transportation engineering, and urban planning. And this is a collaboration between York and Waterloo and a bunch of companies in Ontario. Okay, so again, the problem is we do have all these raw video sources. We have, for example, data from Ministry of Transportation Ontario. We have surveillance cameras in various places in the city, an overwhelming volume of data. And so we have this challenge of trying to move and store and use those data. A big challenge in using visual data for city understanding is the user interface. So if you've ever walked into a security office or a transportation office, you always see something like this. You have a wall of monitors, which are essentially arbitrary 2D projections of a very complex 3D world. And then you have these poor people here who are tasked with trying to make sense of this bewildering mosaic of information. So it's amazing how primitive our visual interface is. for problems that are so important. And then we have a third problem, which is privacy. So one of the big challenges in using visual data to solve problems is that it's unclear whether we can share these data because people can be identified in some of those data. And we have a right to not feel like we're constantly under surveillance. So many challenges in this project, and is that there's an opportunity to solve these challenges through a better understanding of how human perception works. And part of that is the fact that human perception is not just attentive, but three-dimensional. And I think a lot of people in the audience would know what I mean by that, but I still always like to show this great example from Roger Shepard, for those of you who have seen this. So here we have two tables, obviously, that are clearly completely different in their size and their shape. However, they're not. And I can prove they're not by taking one of the tabletops and through a rigid transformation, through a translation and rotation, move it to exactly cover the other tabletop. Okay, magic trick. So that's interesting. So how is this possible? We have two tables that are obviously different, but they're clearly the same. So the resolution to this contradiction is, of course, that equivalence only applies in the two-dimensional plane of this screen, right? And your brain absolutely doesn't care about that kind of equivalence. Your brain cares about the three-dimensional relation between these tables, even though, in fact, they are just a luminance pattern on this 2D plane, but you interpret it as 3D. Okay? So that 3D quality of your perception is not some option that you switch on and off. That's baked in to how you see just about everything in the world. And so we really need to respect that when we build technologies. So how does that relate to this ISOM project? So the idea is we have these video data that are useful because they carry information about dynamics in the urban environment, but they have this challenge that they're 2D and that's not well suited to human perception or cognition. The opportunity, we think, is that we also have, these days, pretty accurate and democratically available 3D geodatabases. And so the obvious thing to do is to marry these into a single system that's both 3D and dynamic. And we think that's important both for human perception and cognition, but also important for analytics. You want your analytics to tell us about what's going on in the real 3D cityscape, not in the two-dimensional plane of your sensor. Okay, so as an example, we're using the York Kiel campus as one of our test sites for this project. And in collaboration with Esri Canada and our geomatics people at York, we're building different kinds of 3D models of the York Kiel campus. And this is a Unity 3D rendering, so you see traffic and pedestrians and so forth. But all of these dynamic agents here are just simulated. So these are just sampled from a generative model. But the ambition is now to fuse that in a seamless pipeline with real-time sensing and analytics. So for example, this building here is called York Lanes, and there's a corridor that runs through it called the Colonnade. And we have cameras that are mounted at either end of the colonnade. And these cameras can be used to image and detect and track the people that are in that 3D environment. And so this is work led by my postdoc Pio Claudio. The idea is to take advantage of a lot of work we've done in the area of online camera calibration. So these are algorithms that can online solve for camera pose and focal length just from the structure and the built environment. And that's critical because it allows us now to take people we've detected and tracked in the sensor plane and then back project those locations through the optical center to the ground plane, where we can instantiate avatars to represent those activities. And so we end up with something like this. Hopefully you can see this. So on the left, we're just running an open source body detector open pose using fairly simple trackers. But the point is more, this part is to geolocate those people in the 3D environment and then represent them as avatars. And now if you're, I mean, this is just a video, but if you're in the lab running Unity 3D, now you can move around in this space as much as you want. You can even assume first-person perspective of one of these avatars. And so the idea is now to try to scale that up to, you know, larger spaces, more cameras, and so forth. So what are the advantages of this approach? So first of all, we're converting to this 3D coordinate frame, which is much more natural for human perception and cognition. But the other thing, of course, is that privacy issue, that as long as the data remain in the raw video mode, that's a barrier to sharing these data and using them to solve these problems beyond critical security. So in particular, if you can imagine a world where we virtualize near the edge, right? So relatively early in the pipeline, we convert that raw data to the 3D virtualization. It solves a lot of problems at the same time. It solves a volume problem, it solves a perceptual cognition problem, and it solves the privacy problem. And that in turn, we think would foster innovation because it means that we can share these data much more broadly. That's kind of my big pitch for this whole idea of attentive video and curated video. All right, that was the appetizer. So finally, we get to the main event, the headline event, which is hockey. In this case, it's still about curation and attention. We're not yet at the 3D virtualization part yet, but that's an interesting direction that we'd like to go. And this is the PhD thesis of my student, Hemant Pitapparthi, who really wanted to work on cricket, but I told him that the hockey market was a bigger market. Okay, so I'm mainly just going to talk about a very simple problem, which is automatic play tracking. But if I have time, I don't know if I'll have time, I'll talk a bit about a second problem, which is automatic play break segmentation. That is, how do you automatically find the periods of active play so you can compress the video? Okay, so play tracking. So what's this all about? So if you are relatively wealthy and you can afford Leafs tickets, then you know that if you get good seats, the rink is actually pretty big, right? So it's subtending quite a large part of your field of view. But the instantaneous play is usually much more localized, right? So as a consequence, you're going to be moving your head and your eyes a lot as you follow the play. Okay, but unfortunately for those of us who can't afford those tickets, we're going to watch this game at home. And it's critical that we have this guy, right? So he's our surrogate who's going to essentially be moving our head and eyes for us, right? He's a professional videographer, and he knows how to move that camera to follow the play. And what gets delivered to us is, of course, the curated video that we can watch on our iPad or whatever, okay? So that's great, except that that model only really works for the elite level of play, right? So for most of the amateur levels of play, it's not economically feasible to hire this highly trained guy and his expensive equipment to do the videography. And I guess as we all know, that the NHL is just the very tip of the pyramid, right? Below that elite level, we have a lot more players, a lot more rinks, a lot more games. In fact, apparently 637,000 registered hockey players in Canada alone, and more than 8,000 ice hockey rinks in Canada. And there's also, we think, a need. So yes, you want to watch professional sports because the level of play is very, very good. But a lot of us want to watch amateur sports because we have a much closer social connection to the players. You know, they're our family and our friends. And, you know, more and more we're living in different cities, you know, but we still want to be able to see those games being played in Vancouver or Montreal. Okay, so the goal is automatic videography for the masses. And let's start with the national sport. Yeah, I was just thinking about that as you said that. Yeah, I'm not sure about lacrosse or hockey. Anyway, a very Canadian sport. Let's put it that way. So, so there is prior work on camera planning for sports, and that work would argue can be divided into two basic categories. So there's a direct regression approach, which is cool. So if you can get your hands on the encoder values for the pan, tilt, zoom components of that are being controlled by a professional human videographer, and synchronize that with the real-time video of the actual game, then you have a regression problem. Then you can actually regress those parameters on the video data and learn a model. And that approach has been tried. And then there's a more classical approach, which we can call the scene understanding approach, which is to take the raw video and then try to infer from that some semantics, and then have a model which maps from the semantics to a control plan for the camera. And that's probably a more traditional approach. So the approach we follow, you could think of as a fusion of those two approaches. So we call this attentive puck tracking, APT. And just to be concrete, so right now the problem we're solving is we start with a 4K video that subtends the entire rink. And we're not going to work at this point on actually moving the physical attentive sensor. We're just going to say, I want to follow the play, and then I want to take a dynamic zoom, digital zoom, of that video and produce still a fairly high quality HD video that's extracted from that 4K video. Okay. The problem is, what is the play, right? That is kind of a critical problem. The play, quote unquote, is not a really well-defined object. And so the solution that we've taken here is to use the puck as a surrogate for the play. So we know that the puck is not identical to the play, but the puck has the great advantage of being objectively well-defined. Okay? So we're going to hypothesize that the puck is close enough to being the play that it's worth regressing it on the data. And if we can estimate where the puck is and do the digital zoom to the puck, that will be sufficient. So that's the assumption. So you can think of this as a fusion of those approaches because we're doing regression, but we're regressing on a scene variable. Okay, so very simple idea. There is actually some work on puck detection, believe it or not, but it's again on this curated broadcast video. So most of the work in sports video is actually on a video that's already been curated by a videographer. Our problem is quite different because we have a much wider field of view. So the puck is very, very small. So in our case, when we do the regression is not really going to use the puck at all. It's actually going to use the context, the players, their positions, their velocities, to indirectly infer where the puck is. All right, so this is just a slide on data sets. So we started this project with quite modest data sets, a couple of cameras and 4 different rinks, 7 games. We've now been, so we have an arrangement with the Canlan Ice Facility at York Kiel campus, and we've recorded all of the varsity games for the men and the women teams this year. So we have a much larger data set now, and so that should help us in doing some more interesting things. But everything I show you is just going to be on these small data sets. So maybe one of the more interesting questions is, how do you ground truth these data for learning? And so the method was, we didn't use Mechanical Turk because we need resolution. So we do the ground truthing in-house. We have a 4K display. We display a 4K video on the display. The observers have a large trackpad and a stylus, and they play a game. And the game is just keep the stylus on the puck. And so, I mean, in the world of psychophysics, this is actually a pretty fun task, but that's kind of a relative statement for those of you who've ever done any ground truthing. Now the problem is still, of course, that we never have absolute ground truth, right? So we have no beacon in the puck. So we actually never know how accurate the humans are at doing the task. The best we can do is just analyze within and between observer consistency across trials of the same visual data. So we use that as a surrogate. And so what I'm plotting here is the RMS deviation, both within and between observers. And this is in meters. So we back project these deviations onto the ice surface. And the one variable we do have control of is the playback frame rate. So the video is recorded at the rink at 30 frames per second, but we're free to choose what we play it back at, right? So we play it back anywhere from 1 to 16 frames per second. And then the idea is we want to play back as fast as possible because we want to get as much data as possible, but not so fast that we start to lose the observers, right? And so we can see here that up to about 8 frames per second, we're maintaining about the same level of internal and between subjects consistency. But then things start to go a little pear-shaped, at 16 frames and above. So what we do in the end is we do record all our ground truth data at 8 frames per second. And there is some, you might be thinking about lag. There is lag involved, certainly, in the human motor system, and we know quite a bit about that from prior work. And this lag, in our case, turns out to be on the order of 125 milliseconds. And so it turns out not to be material in terms of the accuracy we need for this project.
James?
Yeah.
So you could, straightforwardly enough, calibrate the camera.
Yes.
The extrinsic.
Yeah.
And you could show the person a view from above as a result.
That's true.
Than the natural view of the camera.
Yeah, really good question. So the question was, why not rectify the imagery to a plane view? And we've talked about that. Often that doesn't work super well, right? Because when you've got a ground plane with vertical objects and then you rectify, your vertical objects now become super smeared and it's very distracting, right? We actually haven't tried it though for this particular application. In what I say, but what you say makes a lot of sense in terms of the whole setup I gave in terms of 3D perception. So that's certainly where we're going, is to at least understand the 3D projection and take that into account. In this phase, we simply did everything in the image plane for the ground truthing.
Because I was sort of wondering what the relationship between the errors are and where the puck is on the ice.
Yeah.
The ice is in the near boards.
Right. Yeah.
And there are also perspectives.
Absolutely. Yeah, those are all good questions. So we asked the observer to track the puck even when it's completely occluded, right? Yeah. And we haven't really done any analysis of how that accuracy varies as a function of the distance from the sensor or all that good stuff. So yeah, there's lots to do there, because I think there's lots of activity in sports in producing visualizations, 3D visualizations, and it's so much fun to be able to get in there in 3D in these dynamic events, right? So all these questions are important. Okay, so that's the ground truthing. So now having the labeled data is like the key ingredient, right, to almost everything we do in computer vision these days. And the actual deep regressor is not particularly interesting. It's kind of a standard architecture with a series of convolutional layers, series of fully connected layers. The input channels are simply the RGB imagery, optic flow, so we break that into horizontal, vertical optic flow. And we also have a pre-processing hog-based person detector, and then represent detected people as simply as rectangular masks in another channel. Okay, so we have 3 + 2 + 1 = 6 input channels, and this is completely frame by frame. So we've done there's nothing spatiotemporal here, and then the output is simply the two-dimensional image coordinates of the estimated puck location. And again, as Dave was saying, we debated whether to do this all in rectified coordinates or not, and at this point we're doing it in image coordinates. Okay, so that's the architecture, and again, once we have an estimated puck location, we're at this point going to simply crop that to a fixed crop size, so basically a digital zoom. But you can imagine next, version 1.2 would be also adapt the zoom somehow, Then, of course, we need more than the puck location for ground truth. We need some other kind of ground truth measure of what the right zoom would be. Okay. Now, because we have this very simple frame-by-frame system, we have to do some kind of temporal smoothing post hoc. So we can make this causal or non-causal. But because we're not doing any predictive tracking, if we do causal smoothing, then we quickly get, as we increase the time constant, we quickly get lag, right? And the way we're selecting the optimal time constant is by minimizing the empirical error on our training data. So when we try to do that for causal smoothing, it selects a very small time constant. And as a consequence, we get, as you see here in green, we get this very noisy tracker, which is fairly accurate, but it's not very pleasing, right? Because you're seeing, it's kind of a cinema verite, kind of very shaky camera. So what we've done instead is just use non-causal smoothing, where we have a symmetric temporal kernel. And then when we minimize the error, we actually get, fortuitously, we get a very nice, qualitatively pleasing smooth tracker. And the time constant is, as you can see here, sort of on the order of 200 milliseconds. So, that means that it's just like a tape delay of like half a second, and you can have this more accurate non-causal temporal smoothing. All right, and then this is just showing results. So we don't really, there's no real prior work on exactly this problem. So our baseline model is what we call MPP, which is median player position. So just we detect the players, and then it's kind of a follow the herd strategy. We assume the play is where the players are. And that often works, right? But then what about the breakaway play? That's completely the opposite of that, and that you don't want to miss, right? So that's kind of the Achilles heel of that approach. And then these are just various lesion versions of our system that show that all these cues, the player detection, the color imagery, the optic flow, they all contribute to performance, and then the smoothing helps a little more. And then the error that, in this particular experiment, the error we're getting is sort of on the order of 5 meters, which doesn't sound great, but turns out to be satisfactory for this problem. I think the rinks are 61 meters, something like that. Okay, so that's the idea. Just more experiments as we transfer across rinks, so we get an increase in error, but it's still better than baseline. And just example demo here. Okay, so here's an example of how it works. So on the top, you have the original 4K video. On the bottom, you have the HD crop, and you see it does pretty well. We have some truncation of some parts of the rink here, so it's limited to what it can do. But I think you saw there a breakaway play is a good example where a follow the herd strategy would not work, but the system has somehow learned that it needs to follow. I think it's coming up here. It needs to go this way. So how did it do that? Like the answer always in deep networks, nobody really knows. But you can imagine, it could be using like max velocity or something, who knows what the features are. But yeah, so that's the idea. Pretty straightforward. I don't know how we're doing for time. I think I'll just maybe 2 minutes. I'll just for fun briefly talk about other things that we're working, or one other thing that we worked on in this domain. And this was a great project with a very good undergraduate summer student last summer, Michael Dowling, who's a passionate hockey player. So was really excited about the project. So this is the problem where you would like to not only curate in spatial attention, but also temporal attention. So as you know, in most sports, there's periods of active play, and there's periods where the whistle's blown and people are reconfiguring and so forth. And if time is short in your life, then you might want to just see the former and not the latter, right? So that motivates an automatic system that can automatically excerpt those periods of active play. I won't go into details here, but the idea is there's kind of complementary cues. There's visual cues, which we think is primarily the player motion. But there's also an auditory cue, which is the whistle. The problem with the whistle is it tells you that there's a change of state, but it doesn't tell you, which state you're going from and which state you're going to, right? So the idea is you really want to combine these two cues together. For motion, what we do is simply integrate optic flow, but selectively within player positions. And then the other just little trick we do is we take a Minkowski sum, which gives us a little more flexibility. And we know from a lot of prior work that it's often very helpful to do that, and then to optimize this exponent p. And to just give you an example, for this case, we're just measuring the empirical error on the training data as we vary p, this Minkowski exponent. And what we find, which we find in motion many times, is that the best thing is to drive p to infinity. And so the empirical fact is that the best thing to do is just measure the maximum speed. And that is your cue to whether play is active or not. So it's kind of, it's very, very simple, but that's what the data say. Yeah, so then the missile part, I'll just skip over that. That's not too interesting. The last thing I'll say about this is it's fun to think about what you want the state machine to be, what you want the hidden Markov model to be. You would think, oh, it's pretty obvious. You have two states. You have an on state and an off state. But actually, that's not so great because the whistle is this very punctate observation, right? So what you really want is 4 states where you have a state where you have the emission process is about the whistle, and that really accommodates your observables really well. So you have these transition states of off, start whistle, on, stop whistle. But that's still not quite perfect because hockey players can't accelerate and decelerate instantaneously. So it actually turns out to be useful to at least have 6 states where you have not only the whistle state, but you also have this transient acceleration state and then a transient deceleration state. So these were kind of fun things that we learned through doing this project. Other than that, it's just a straightforward hidden Markov model. So you can use the Viterbi algorithm. So again, the assumption is it's non-causal. So you could record the whole video and then compress it, or you could divide it into tranches and then knit it back together. But so you have the whole sequence of observations, and then you want to find the most probable configuration in this case. Okay. All right, and I can show an example. This is just showing the kind of results you can get. So best to look at this slide here. So here we're plotting the amount of compression we can get in time as a function of how many of the frames of active play have we missed, right? So you want to be up here, right? And the good news is we can get about, even in this very simple system, about 25% compression and not drop any frames on our test data set. Okay, and so this is just a demo example. So this should the big letters here should actually, it's the camera state, so it should say either camera on or camera off. So here it's camera off. And this is the 6 state, well, the small text here is the 6 state system. And so what you can see is the way it's engineered is that it's conservative, so it will move into the play state, the camera on state, typically before play begins. And then it will typically stay in the play state a little bit after play stops. And that has to do partly with a loss function that we've used, which is penalized misplay more than inclusion of non-play. All right, so that's just another fun example of things to do with hockey. So lots more that could be done. Of course, integration with the attentive sensor, the hardware. So one of the things that can't be as easily done with digital zoom, of course, is reduction of motion blur. Now, there's lots of cool work on eliminating motion blur digitally, but optically is always better if you can do it. But also just getting a higher resolution product. So now we're getting a 720p product, and for some people that wouldn't be enough, right? Be cool to do designated player tracking. So you show you indicate who your favorite player is, and now you get a bespoke video, which is based upon that player. Could be your daughter or your son. Or you want to be in the game, right? So you want to actually virtualize the game and then select your point of view, including possibly first person. So lots of fun directions. All right, thanks. So that's it for the talk. So just to summarize, so I tried to make a big pitch for what I'm calling different use cases, security, understanding. Finally, this, but part of that pitch was this idea of virtualization, 3D virtualization also has merit in terms of solving problems like privacy problems. Okay, thank you. Hi.
So figured out truth.
Yeah.
My understanding following like a continuous person drawing as the function.
That's right.
Having like a version where you show the person skip forward a bit here.
Yeah.
And like straight line. And you can imagine you just draw the straight line.
That's a great idea. Yeah. So the question I don't know if I've ever heard is to accelerate the ground truthing by essentially selecting keyframes and then being able to interpolate between them. So a couple of things about that. I mean, I like where you're going. The reality is that you do much better ground truthing from the dynamic video than you do from static video. If you stop the video, it's really sometimes hard to know where the puck is, especially if you land there from some other time. Okay, so that's one limitation. Then the other thing is you need to have a really good way of selecting those 2 points in time where there aren't strong nonlinearities in the puck trajectory, right? So that's what's interesting about this problem is that it's very nonlinear. It's a kinematics thing where the puck is bouncing off things, right? So that would be, you had a way of somehow reasoning about that with respect to the 3D environment of the where the players are and where the boards are, then you could, in some cases, reason that, okay, between these, like I know where the puck was here, based upon the based on the human label ground truth, and I knew let's say somehow I knew its direction, then I could be safe for a certain amount of time, right? So it's.
I think one way is if you realize that it's not the same trajectory, you choose some other frame in the middle. So
Yeah, that's true. So you could reason backward, you're saying? Yeah, that's a cool idea. Yeah, getting quantity data is part of the puzzle for sure, because it's hard to perk because we want people to have high resolution. So that's a good idea. But in general, a lot of the way that ground truthing is done, typically for a lot of problems, is click by click, right? And so moving to these motion problems is fun because you're getting in our case, eight data points per second, in a sense. So it's fast in that way. Sure.
You showed something like kids with the rectangle.
Yeah. Yeah, great question. So the question was, can we do smooth pursuit? So we're doing saccadic gaze control. And we have worked on it. I've never had the student that got really passionate about smooth pursuit. It's a much more interesting problem, right? Real-time control problem. And so that's the goal, certainly, because we need that if we're going to add the hardware into the hockey project, for example. Interesting problem because you have delay, significant delay, in getting the visual data into whatever processor you're using. And that's probably going to be on the order of more than 100 milliseconds. And then you have this very nonlinear kinematics in the rink, right? And so there's a lot of opportunity for reasoning in that process. And then the other thing is that the human smooth pursuit system is really fascinating and also subject to very similar delays. So lots of interesting dimensions. So I keep trying to get a student excited about that, but we haven't. Yeah.
Professional level, there's a lot of it. And like sometimes the cameras are and do you have
Yeah, it's a really good question. So we've kind of solved an easy problem because we were able to clearly objectify the goal as the puck, right? So that's partly why the regression on the videographer encoder parameters is really nice, because you get whatever the art, if we think of the videographer as the artist, you get whatever the artist, the expert artist does. Another cool idea is to put eye trackers on people who are there in the stands with synchronized video, even head trackers, or just the video. And so that would be a nice way, let's say, of augmenting what we have, right? So, and that's not impossible, right? And we could certainly recruit give people free tickets, free Leaf tickets, and get them in there with trackers and GoPros and stuff.
Okay, let's thank James.
Okay,
again.
thank you.
Thank you.